Regarding the concept now that talks about electromagnetic induction, the idea here it's similar to the previous concept, but here we're gonna have a wire instead of having a current carrying wire. So in the previous lesson we had a wire. This wire must be a wire connected to a source, could be a battery or any source of electricity. But now this wire is not connected to a source, but instead it could be connected to a bulb or a voltmeter that shows the pointer. When the pointer is deflected, this indicates the amount of electric current. Now, how electric current will be induced in this case? If the wire is connected to a voltmeter or a bulb and there is a magnet that moves into and out, or there is a relative motion between the magnet and the wire, EMF is induced, which automatically current is going to be induced. So in this case we have a wire. This wire is connected to a voltmeter, and regarding to this scenario the magnet is going to move in and out. So there is a relative motion between the wire and the magnet. That this means EMF is going to be induced automatically. Electric current is going to be induced. That's why the pointer of the voltmeter will be deflected. While going to this case, so in scenario 1 magnet was in motion, while here in this scenario wire is going to move up and down. So again we're going to have a relative motion, but the wire moves up and down, and this will induce EMF, which automatically current will be induced, so the needle will be deflected. That shows that electric current is generated or is induced. Going to the question here, the first question that talks about the idea. Now here this scenario shows magnet and there's a wire, but this wire is a normal wire, is not a current carrying wire. Due to the relative motion, we need to know where is the direction, where the wire exactly will, to which direction the wire will move. Which rule will be used here? The Fleming, but in this time it's not a Fleming left hand rule, but it's a Fleming right hand rule, which is kind of similar to the idea of Fleming left hand rule, but here similarly thumb shows the current and first finger shows the field, which is the magnetic field, and this is the current. So going to the question here, magnetic field direction is, we know it's out of north into south. So this is the field, out of north into south, and obviously this is the direction of the current, which is goes out of the page. So using Fleming right hand rule and the current out of the page, so motion will be toward C. Here same idea, but here in which direction must the wire be moved to induce EMF across the two poles of the magnet? So here we have a wire between the two poles of the magnet, has to be moving in a specific direction in order to create a magnetic field or induced EMF. So obviously we're going to eliminate options. So QR will be eliminated because we have to choose the direction that represents a perpendicular motion, which is OP. Okay, going to the idea of a generator. A generator relies on the concept of electromagnetic induction. As we can see here, we have when it rotates, the position of the wire changes. Automatically, the amount of induced EMF is going to be changed. So this sketch shows we have two positions. The first position is here. This shows the smallest, it's going to be 0. The smallest EMF will be when it's vertical or perpendicular. So when the position has to be perpendicular or vertical, this case we are going to have 0 EMF. But if the position change, the position of the coil will be horizontal or parallel. This shows the greatest amount of EMF, which can be represented by these 2 points. So here in this question, in AC generator, a coil is rotated in a magnetic field and an electromagnetic field, which is EMF, is induced in the coil. In which position the coil does the EMF have the largest value? So again here, the largest value, the greatest value has to be horizontal, which is this case.